So we're now going to look at solving systems of equations using matrices. I'm going to look at, first of all, how we could use it to solve simultaneous equations. That's an application of matrices, which is quite useful. And also what that looks like in a 3D space and what that actually means for the matrices that we are working with. So let's just have a look at this first point here. So this is the basis of how we're going to solve our simultaneous equations. So if I just look at the thing in the sort of yellowy box, and we'll just explain it. Basically, it says, so matrix A times by xyz will be equal to V, and therefore the matrix xyz would be equal to the inverse of A times by B. So just to sort of give you a bit more there. So basically, if we think of it like this, so we have our matrix A multiplied by x, y, z, and we're saying that is equal to V. Well, we know if we multiply both sides on this side, remember it's not commutative, so it has to both, if it's on the left on one side, it has to be the left on the other. And I need it to be on the left because I need these two to be next to each other. So we should know that basically an inverse times by its matrix is going to be the identity matrix, which is basically just 1. So we can get rid of that, and then we can see there we have xyz is equal to the inverse of A multiplied by B. And that's the basis of how we're going to solve these simultaneous equations. So let's have a look at this example here. So using an inverse matrix to solve the simultaneous equations. So yes, you could do it an algebraic way, but it literally says if it asks you to use an inverse matrix, you need to use an inverse matrix. So what we're first of all going to do is we're going to write it out using a matrix multiplication. So that system of equations, we're going to write it out in matrices. So what I'm actually going to do here is I'm going to first of all write a matrix out with the coefficients of x, y, and z. So I have a minus xs, so that will become a minus 1, and then a 6y, that will just become a 6, and then minus 2 because I've got minus 2z, and then it will be 6, minus 2, and minus 1, and then we'll have minus 2 there, a 3, and a 5 there. And then I'm going to write that multiplied by this matrix here, x, y, z. And I'm hoping we should be able to spot that if I multiply that out, that would give me the, the left-hand side of all three of those equations. Because if I look at the first row, multiply that by the first column, there is only one column. Minus 1 times by x will give me minus x. 6 times by y give me 6y. Minus 2 times z give me minus 2z. And then we're going to write that equal to the right-hand side. 21 minus 16 and 24. So that's how we're going to write out our system of equations using matrices. And if you multiply that all out, you get those three systems of equations there. So if we multiply that left-hand side, it's easy. This gives us the equations, which is what we just said. So now we need to find the inverse of the left-hand side matrix. And that basically is it's looking at this thing here, where we can see if we multiply the left-hand side by the inverse matrix, we'd just be left with x, y, z, which is what we want. We want our solutions. So we need to multiply both sides by that inverse matrix A. So first of all, we need to find that inverse matrix. So I want the inverse of the one on the left-hand side. So just to make it super clear, I want this, and you would be expected to use your calculator. I know you should be able to find the inverse of a matrix without a calculator, because you could be asked algebraically to do it. I mean, it could have algebra terms in it, but you should be able to do this on your calculator. So I'm just going to do that right now. So when I do that on my calculator, I get that lovely thing there. I'm assuming you can take out a factor of 1 over 189 out of all that, but I can't really be bothered, so I'm just going to leave it like that. So we use our calculator to find that, and then we need to think about our final steps here, because we found the inverse matrix. So I'm actually, just for ease, I'm actually just going to call that matrix A inverse, just so I don't have to keep writing out that inverse matrix over and over again. So x, y, z, as we said, if we multiplied by that inverse matrix, as we can see here, we know that the matrix A would cancel, well, it wouldn't cancel, it give you the identity matrix, which is just 1. So therefore, xyz is equal to the inverse matrix multiplied by the matrix that was on the right-hand side. So that is going to be, give me a pen, thank you. So it's going to be the inverse matrix there multiplied by our 21 minus 16, 24. So we just need to multiply those two things together now. So just going to do that on my calculator, and you actually can go straight there. You don't need to, unless it asks you to write I would write what the inverse is anyway, but you can just go, you can literally write on your calculator that inverse matrix multiplied by the matrix on the right hand side, which is what I'm going to do rather than retyping all that in again. And I get that equals -1, 4, and 2. So that means that x is -1, y is 4, and z is 2. And you can check that if you would like using the simultaneous equation solver. So we know there's other techniques that you can use. You can use algebra, you could use the solver on your calculator if it does that. But remember, if a question asks you to use inverse matrices, you need to show that you've used inverse matrices. But yes, you could use the solver tool to check that in an exam setting if you wanted to make sure that you were definitely correct. So this question, it might not at first look like it's a simultaneous equation question, but you might get questions like this where it's more contextualized and you need to figure out that you need to form a system of simultaneous equations and then solve them. So here we have a colony of 1,000 mole rats. It's made of adult males, adult females, and youngsters. Originally, there were 100 more females than adult males. So we have the number of adult males after 1 year increased by 2%, number of adult females increased by 3, youngsters decreased by 4, the number of mole rats had decreased by 20. So use and form and solve a matrix equation to find out how many of each type of mole rat were in each colony. So as it says to start with, let x be the number of males, let y be the number of females, and let z be the number of youngsters. So we have these 3 statements here that we picked out from the information we're given, and that is so we can form different equations. So it says here we have 1,000 mole rats total. So let's think about what equation we can form. Well, we know we have males, females, youngsters, and we know that adds up to 1,000 total. So the first equation that we can have here is that x plus y plus z is 1,000. So that's the first equation that we can write there. Okay, so let's think about what else we were told. So we were told originally there are 100 more adult females than males. So the way my brain would process that, and we'll use a different colour. So if I take the number of males and add 100 to that, that would be equal to the number of females. Originally there are 100 more adult females than males. That's what it's saying. So if I take x at 100, that gives me the number of females. I want it so all the letters are on one side and all the numerical values are on the other side. So I would just literally rearrange that and say that y minus x is 100. Now notice here there's no z term, but does there need to be a z term? Not in all 3 of them. You're going to need to have a z term at least one other equation, but you don't need it in all 3 of them. So that, I should probably colour code these. So that's that one, and then the red one was that one. And then let's do green for this one. So the total mole rats after 1 year decreased by 20. So let's think about what we could do with that information there. So we already know that we know the increase in all the populations. So we know after 1 year we had increased by 2% males. So that means we have 1.02x, doesn't it? Because 102% as a decimal, 1.02. The number of adult females increased by 3%. So that would be 1.03 of our y value. And then it says the number of youngsters decreased by 4%. So that would be 0.96z. And it says the total decrease by 20. So that would be 980. That would equal. if I can do 1,000 minus 20 in my head. So they, I believe, are our three, I'll just zoom out a bit so you can see them all. They would be, I believe, our three systems of, our three equations there. So yes, there's 1,000 in total, I was just checking that. So we have our three equations. So now, that's probably the most difficult bit of that question. And then it's just a case of writing it in a matrix and then solving it. Obviously, if it doesn't specify you need to use matrices to solve it, you can use whatever works for you. But since we're practicing matrices, let's maybe do it as a matrix. So let's first of all just write out our equations as matrices. So we have, so I'm going to do the top one. So xy plus z is 1,000. So it'll just be 1, 1, 1. And then it will be a, so it's y minus x. So it'll be a minus 1, a 1, and a 0 there because there's no z term. And the bottom one will be, this one might run out of space, 1.02. So I'm trying to write it so they all line up. 1.03 and 0.96. I don't know why I thought if I like, I don't know. So that is my, I say my equations, it's not because I need to write the x, y, z there. So they would be our, I've tried to create that z, it really didn't work, did it? So they would be our equations written as matrices if I actually write what they equal. So the first one equaled 1,000. The second one equaled 100. And the third one equaled 980. I have no idea why I made that bracket so huge, but I did. So there's our equations written as matrices. So now the next step, if I can scroll, there we go. So remember, we need to then just find out what the inverse of this matrix is here, because we're basically going to multiply both sides by the inverse of that matrix. And you can follow the steps that we did before, but you're effectively going to end up with this, that x, y, z will be equal to the inverse of that. You know, I'm going to write the bottom row first because that takes up the most space. So the inverse of this matrix here, inverse of that, and that's multiplied by 1,000, 100, 980. Just tidied that up so that was a bit easier for you to see, but that will give me what x, y, and z are. So I just now need to put that in on my calculator. Okay, so typing all that in on my calculator, spoilers for what's coming ahead, that gives me that x, y, z equals 100 to, that should be a, sorry, there we go, 100, 200, and 700. So let's just check what the question actually was, because I know we found the values, but there we've not actually, we have found it, but we haven't actually specified it, if that makes sense. We just, it's in matrix form. And I would always say treat the examiner like they're an idiot and spell it out, because the question actually asks us, find out how many of each mole rat were in the original colony. So that is what we've done, but we haven't actually said that. So you probably, at this point, even though we've done all the maths, you probably would lose an answer mark because we've not actually technically answered the question. So we just need to write that out fully. So let me just zoom in a bit. So we have, based on our set of equations, we have 100 adult males. So 100 adult males. We had, sorry about my writing, it is atrocious, 200 adult females. And then we have 700 youngsters. And then a quick sense check. Obviously, you could put this in on your calculator and do the solver tool like that. But obviously, we weren't given the simultaneous equations. We set them up ourselves. So another sense check you could make to check, you know, that you actually set up the right simultaneous equations to start with is think, well, let's think about what information I was given at the start. We were told there's 1,000 mole rats. Do our totals add up to 1,000? Yes, they do. So that's probably a good goal. And then obviously you could sub in your values and check that they all work. But I'm happy with that, and it adds up to 1,000. So now we're going to talk about this thing called consistency of linear equations, and then we'll have a look at it when we have it in 3D and we're dealing with planes. So as it says here, you should already be familiar with the idea that the solution of a system of two equations can be visualized by finding the point of intersection. So that is assuming that they are consistent, which is what we'll talk about now. So a system of linear equations, in bold, is known as consistent if there are at least one set of values that satisfy all the equations simultaneously, because that's how simultaneous equations work, which basically means there's at least one point of intersection. So here we have two equations here. X plus 2y is 1, and 3x minus y is 0. So we can see that if we plotted those lines on axes, they intersect at that singular point there. So they are consistent because they give us a solution. So the idea is if the equations give us a solution, they are consistent. If they do not give us a solution, they are inconsistent. So that corresponding matrix, and this is sort of, it's a bit of a confusing idea to get your head around, but it hopefully will make more sense the more we talk about it. So that corresponding matrix there, which is just formed from those two lines. So we can see 1, 2, 3, 1. Well, the 1, 2, let me get a pen. So that 1, 2 there is that x plus 2y. And then in blue, the 3x minus y is that 3 minus 1 there. So that matrix is non-singular because you could find the inverse of that matrix there. So we'll talk about singularity because I said it meets at a single point, but it's not singular. But remember, singular means it doesn't have an inverse. Non-singular just means that it has an inverse, and we could find the inverse of that matrix because it has a point of intersection. And this is the key thing. It has to have one point of intersection to be non-singular. If it has no points of intersection or it has multiple points of intersection, it is a singular matrix, meaning it does not have an inverse. So if it helps you think about it in terms of inverses, that might be easier. So if that's one point of intersection, it has an inverse. If it has many points of intersection or it has no points of intersection, it will not have an inverse. So let's have a look at these other 2 points. So we have here x minus 3y is equal to 1, x minus 3y is equal to 2. And we can see there that they form 2 parallel lines. And hopefully that makes sense because the x and y coefficients are the same, but their y-intercepts are essentially different, 1 and 2. So they are parallel to each other, and they would be inconsistent because we know parallel lines, they don't meet each other, they don't get any further apart, they don't get any closer together. So they are inconsistent, meaning they have no solutions. So that matrix is singular because, as I said, it doesn't have an inverse because it doesn't intersect at one point. So again, singular, it gets a bit confusing, but it doesn't have an inverse. That's what we're trying to convey with that. So parallel lines will not be consistent. There's no solution that satisfies both of them. And then we finally have this situation here, which is a bit hard to show you. So I'm gonna try, I'm zooming in a lot here, just to sort of show you what I mean. So we have x minus 3y is equal to 1, 2x minus 6y is equal to 2. Now you might think they're parallel, but they're close together. They're actually not. If we think about when you're solving simultaneous equations, you're trying to eliminate terms, aren't you? So you might form new equations. So hopefully we can see here, so this was equation 1, so this was equation 2. If I took equation 1 and multiplied it by 2, can we see that gets me equation 2? They are the same equation. They are the same equation. Or consequently, if you divided equation 2 by 2, you get equation 1. So these are on the same line. So they're consistent because they're the same line. So they don't just have one point of intersection, they have an infinite number of intersection points on this line. Any point on this line is a solution to that equation because it doesn't matter what you sub in, it'll work, basically. well, not whatever you solve in, but if you put, there's infinite number of solutions all on that line. So the system of equations is consistent because there are multiple solutions. It says there are infinitely many solutions because it's anywhere on that line. So that matrix, again, the matrix formed by the coefficients of x and y, that is singular because, again, if we think about inverses, it doesn't have an inverse. There are infinite solutions. There isn't just an inverse to that matrix because it have to meet at a singular point for that to happen. So if it has many solutions or no solutions, it doesn't have an inverse making it singular. If it does have a single solution, it has an inverse, meaning it is non-singular. Again, I know you think singular point, singular matrix. It doesn't work like that. Sorry. And then we'll have a look at when we have three variables. So now we're looking at 3 dimensions. So it says here in chapter 9, so if you've done chapter 9, you'll know all about this. So it says ax plus by is c gives the equation of a straight line. And then ax plus by plus cz equals d gives you the equation of a plane. We're now talking about 3 dimensions. We have the x, y, and z directions, which give us 3D. And like we talked about the 2D ones, and this sort of helps us visualize what's going on with 3D, we can see sort of what if the matrices are going to be singular and what their intersection points are going to look like. So there are 5 different scenarios. There are 4 here, there's 1 below. So we'll talk about this. So we have scenario 1, which is basically the equivalent of the first one on here, which is basically all the planes. So they're called planes now because they're 3 dimensions, not lines. They all meet at a single point. So we have here, we have 3 planes here, and that black dot is where they all intersect. So that means that they are, first of all, are they consistent? Yes, they are. So consistency means that there is at least one point where all the equations are satisfied. I say at least one because there can be more than one. So, as it says there, they are consistent. Oops, I didn't mean to draw there. They are consistent and they only have one solution, which would mean that it is non-singular as well, just to sort of clear that point up as well, because it has one single solution. The inverse of that can be found as well. So the key thing, it is consistent because there is at least one point where all those equations are satisfied, and it's non-singular because there is only one point of intersection. So you could find the inverse of that matrix. Right, and then we have a sheath of planes. And that is, again, similar to the second, no, it's not similar to the second scenario on there at all. It's not. It's more similar, sorry, to the third one on there. So where we have, they're not the same line specifically, but they all intersect on a line. So as you can see there, so this is called a sheath of planes. So the sheath basically means there is a single line of basically where all the planes intersect. So it says that they have a line of intersection consisting of infinitely many points. So like we had here with an infinite number of solutions on that line, same with this one. There is an infinite number of solutions where all 3 equations of those planes are satisfied on that line. So they all come together at a singular point. And I'll show you this on GeoGebra. There's quite a nice tool on GeoGebra that shows this quite well. So they have a line of intersection consisting of infinite endpoints. The system of equations, again, is consistent because there are solutions. There are many infinite solutions, but there are solutions. And as said before, because it's got infinite number of solutions, you cannot find the inverse of that. So that would be singular. That'd be singular. So, as we said, just be careful about that definition. Then we have planes which form a prism. So this one's a bit hard. There's not really, I guess, a 2D equivalent as much for this one from the scenarios we saw before. So when the planes form a prism, it means they intersect in pairs. So let's just label these, for example. So I'll label the green one, plane 1, the blue one can be plane 2, and the orange one, plane 3. So there is a point here where 1 and 2, no, this is 1 and 3. So this is where 1 and 3 have a consistency, they have solutions, but they do not, if we put those solutions in for plane 2, it will not work. And then same for here. Here we have 1 and 2 here have solutions which satisfy both those planes, but they do not satisfy plane 3, the orange plane, they don't satisfy them. And then same thing with this one. 2 and 3 have solutions which satisfy both of them, but they do not satisfy plane number 1. So they, as I said, they intersect in pairs. So the equations or the solutions will be consistent for 2 of the equations, but not all 3 of them. So there's no point where there is consistency for all 3 planes, where a solution satisfies all 3 planes. So they have no solutions. It's inconsistent, meaning that would also be singular. You could not find the inverse of that because you need a single point of intersection. So that's a prism of planes. And then finally, we have 2 or more planes that are parallel and non-identical. And that sort of marries up with this idea, the middle one of this one, where they're parallel. So you could have 2 planes that are parallel, or all of them could be parallel as well. So you could get, I'm terrible at drawing. I don't know if my skills are up to this, but you could have something. I really should draw them at an angle, shouldn't I? Hang on. We'll try again. But you could have something sort of like this, where all 3 of them are parallel. Like that. So you could have 2 of them being parallel, or all 3 of them being parallel. So they are inconsistent, because again, there's not one solution that's going to fit all 3 planes. So in this scenario, the orange plane will have solutions with the green and blue planes separately. So green and orange will have a set of solutions. Orange and blue will have a set of solutions, but there is no set of solutions which satisfies all 3, because green and blue here are parallel. So there are no solutions between either of those planes that will work because they're parallel to each other. So like before, because those lines, or planes in this case, do not meet, we can't get a solution for them. There's no values that will work for that. So again, it is inconsistent, because for it to be consistent, it'd have to work for all of the planes. So it doesn't. It may only work for like intersection of one plane with another plane, but not all of them. They never intersect, and the equations can't be satisfied. So I'll come back to the bit in the little box in a minute, but again, that would mean that it's singular. You couldn't find the inverse of those matrices. And it says any rows in the corresponding matrix are multiples of each other will be parallel. So it's the same idea as this here, where well, it's similar to, so even though these ones are parallel, so let me show you what I mean. Because it could be, for example, so these 2 here, even if I made that 2x minus 6y, as long as it didn't equal 2, so say if it equaled 5 there, they would still be parallel to each other, because it's just their y-intercept that changes there. Their gradient is the same, it's just their y-intercept that changes. So for that situation, this would also form another parallel line. So it's the same idea, but in 3 dimensions. So if the coefficients of x, y, and z are multiples of each other, but their y-intercepts wouldn't be, or the bit at the end that it equals wouldn't be consistent if you multiplied them, that would be parallel. So as I said here, these are not the same line, because it should be 2x minus 6y is equal to 2, but I've written 5 there, so it's changed its y-intercept, meaning they would not be the same line anymore. They would be parallel lines, but they wouldn't be the same line. So we've got one more scenario here, which is basically this scenario here, where they are the same line. So this scenario is they are the same plane. So the planes are represented by equations that are equivalent. So system equations are consistent. There are infinitely many solutions. So basically the planes are the same. So it was similar to what I was talking about before here, where these lines on the right are the same line. They're just multiples of each other, but their y-intercept bit is also scaled up as well. So for parallel, the y-intercept bit at the end wouldn't scale up. If they're the same line, it would scale up. So these are the same plane. So they'll just be multiples of each other, those planes. And again, that would be that would be singular. I'm getting confused now. That would be singular, because, again, you wouldn't be able to find the inverse of that because there are infinitely many solutions. Okay, so this is just a bit of a summary to sort of help you picture and think about what's going on here. So consistency means there is at least one point where all the planes meet. So they can either meet at a single point, they can meet along a line, which forms that sheath, or they are the same plane, which means that any point that you pick on that plane would be an intersection point. And then inconsistent means there is no solution for all three. So two of the planes could have a solution and another two planes could have a solution, but all three will never meet at the same point. So either that is a prism where you get pairs, so there's consistency between two planes but not all three, or you can have parallel planes where at least two of the planes are never going to touch each other because they're parallel to each other. You might have one intersection here, so you can either have one here where orange intersects green and blue, or you can have they're all parallel, so they're never going to touch each other. So we're now going to have a look at this exercise. I'm going to use GeoGebra to help explain a few things. So it says, decide what geometric situation each set of equations represents. Check the determinant of the matrix. If it's not 0, they meet at a point. So remember what that means. If the determinant is 0, then that means it's singular. So the determinant is not 0, it's non-singular, meaning it has an inverse, meaning it must be intersection at a point. Planes meet at a point is the only time the determinant will not be 0. For all the other situations, the determinant will be 0. So if it has a determinant, they intersect at a singular point. If not, it's one of the other situations. Solve the equation on a calculator to decide if it has one solution, so it meets at a point, but if you know the determinant, we don't need to worry about that. An infinite number of solutions or no solutions. And it says there, infinite means it's either a line of intersection or the same plane. And then no solutions that are either all parallel or they form a prism. And then it says use algebra to see if they are consistent or inconsistent, meaning that you can get solutions for all of the equations. So let's go through these. So it says check what the determinant of the matrix is. If it's not 0, they meet at a point. So you can do this on your calculator. I've just done it on GeoGebra. So I put my matrix in and it told me the determinant is 0. So we know straight away that means that it is singular. So we know that to start with. So I'm just going to write a little S for singular there. So we know, therefore, it's not going to be, they're not going to meet a single point. They're either going to have infinitely many solutions, so a sheaf, or they are the same plane, or they are going to have no solutions, being inconsistent, meaning they're going to be parallel to each other or form a prism. So it says here now, solve the equation, decide if it has infinite solutions or no solutions. We don't really need to worry about one solution because the determinant tells us that. So I, again, just put this on GeoGebra Solver tool, and it gave me this lovely thing here. Now, this is very complicated. On your calculators, I think it's a bit nicer. But basically, we see here, it says Z is Z, and then Y is basically a multiple of Z, and X is basically a multiple of Z plus something else. That basically means it's got infinitely many solutions here. That is what we're saying. There are infinitely many solutions there. So that is telling us that it's a sheath or it's a plane, because there are infinitely many solutions. Again, I'm just going to write a little I for infinitely many solutions. So we know that. So it's now either a sheath or a plane. We need to decide what that's going to be. So remember, if it's a sheath, then they will have one line of solutions. If they are, if they're the same plane, then they are the same equation. So let's think about what's happening here. So it says use algebra to determine, we don't need to worry about that, we know they're consistent. So what I would suggest is we'll have a look at these equations and hopefully can see here, if I think about that equation and I doubled it, can we see that that's effectively the same equation, isn't it? They are the same equation. And then if I took my initial equation, and call that equation 1 and multiplied that by 3 this time, they're the same equation again, aren't they? It's the same equation, it's just been scaled up or down, which would mean they are the same plane, aren't they? They're just all the same equation. So that would be a plane, if I can write that. So that first one is a plane. I'm just going to show you on GeoGebra what that'd look like. So I have this, and you can play around with this yourself on GeoGebra. If you go on Calculator Suite on GeoGebra, it makes it a bit bigger, and 3D Calculator, you can have a play with this and have a look at the planes. But can you see when I type all those three in, and I can make that one disappear, and I can make that one disappear. So there's equation 3, or plane 3. There's equation 2. See, it rests on top of it. I can turn it around, do whatever I want. It's the same plane. And then same with that one. It's the same plane. So we used algebra and the determinant and all that to work that out, but we can see there that it's the same plane. So now let's have a look at the one below that. So I found the determinant of that, and that gave me a determinant of 1, meaning it's non-singular. So there I'm going to write non-singular, so therefore I know they have to intersect at a point. So they intersect at a point, and I know the point where they intersect is going to be the solution to those simultaneous equations. So I know they're going to be consistent, but I can do that anyway, go out to find the point of intersection. So I get that they intersect at that point there. So they're going to intersect at, see if I can actually write this. So they intersect at -66, 21, and -29. And you'll get that by just solving that system of equations, and they intersect at a point. And I just want to show you on the 3D planes, because it's quite interesting to look at. So all this, I'll explain in a minute what I've done here. But there are my 3 planes. And at first you might think, where on earth is this point of intersection? Because what I've done here is these blue lines down here, that is the intersection of the planes. So there's 3 lines here. So I have these blue lines. I should have probably made them different colours, but anyway. We've got plane 1 and plane 3, plane 2 and plane 1, plane 3 and plane 2. So those 3 lines show you the intersection of 2 of the planes. And the idea is that if they intersect at a point, all those 3 lines should meet at a point. And it doesn't look like they do here, does it? But you have to basically zoom out, and there, hopefully you can see that ABC, because I had to do it for each line, there's that point of intersection right there. And you can see, so F, G and I are those lines, so if intersected, the intersection point of those lines always comes back to that -66, 21, 20, -29, which was the solution to our set of equations. So that was intersection of a point. So now we'll have a look at the one underneath that. So I found the determinant. So the determinant is -54, meaning it's non-zero. So therefore I could write it's non-singular, but I know that means it's going to intersect at a point. And then we just find the intersection by using a solver tool. So we get that it intersects at this point here. So 0, 1, 0. So there's my intersection at a point. And then again, we can look at that on GeoGebra. So here are my 3 planes. And remember, the lines are the intersections of the planes. And you can see they all, this one's a bit easier to see, they all meet right there, don't they? Because it's at 0, 1, 0. So it's just 1 in the y direction. Everything else is 0 right there. And you can see those lines, intersection of the planes, all intersect at that 0, 1, 0. So that's the solution to my equation. So now let's have a look at the top right equation. So for this system of equations, let's first of all check its determinant. So its determinant is 0, meaning it's singular matrix, meaning it's either got no solutions or infinitely many solutions. So we know that straight away. So then if we use our solver tool, we get nothing. So there are no solutions. So therefore it's inconsistent. So therefore, I'll just put no. Oops, that should be a no. So no solution, that should say. So that means we're either looking at, is it forming a prism, or have we got things that are parallel to the plane? So when we're looking at things that are parallel, remember what we said up here. If they're parallel, basically the bit on the left hand side of the equation will be a multiple of the other one, but on the right hand side they won't be consistent if you scale it up. So both sides won't scale up to the same thing. So let's see what we've got here. So here we have, so equation, the top one, we have 4x plus 3y minus 2z. Can we see that this equation here and this 8y plus 6z, sorry, 8y plus 6y plus 4z, they are going to be parallel to each other. Because if we multiply equation 1 by 2, we'll get the left-hand side will be the same, but 5 times by 2 would get us 10, whereas equation 3 equals 9. So here we've got parallel. So no solutions, and because one equation is parallel to another, it's going to be parallel. Try and write that in as neatly as I can. It's not going well. That they would be parallel to each other. And I just, again, want to show you on GeoGebra, it looks quite interesting actually. So let's have a look at what that's going to look like. So this is what we get on GeoGebra. So as you can see, it's kind of almost hard to see all three planes. So we have our yellow plane here. We have this like grey plane, and the other side you can see the red one there. Now you might think they're the same, but we already know they're not the same. So they're very close to each other, and I can try and zoom in, but I'm not getting much luck here. They're very close to each other, but they are not the same plane, meaning that they're never going to meet, they're never going to touch, which is why you get a bunch of question marks here. For equation 3 and equation 1, as we said, they're the parallel ones. There's no line of intersection there between them because they're parallel to each other. So that means we don't get any intersection of any of the points. So they're parallel to each other. So let's have a look at the one underneath that. So you might notice this looks a little bit different. It's because I made a mistake doing the second one on the right. So I'm having to do this one again because of that. So I've started by, same as I've done the other times, putting that into my determinant and seeing what happens. Just check I've got it right because I inputted it wrong and that's why I got the wrong thing when I did it the first time. So I get a determinant of 0. So that means I do have a singular matrix here, don't I? Because I've either got infinitely many solutions or I've got no solutions. So let's have a look at my solver to see how many solutions I've got. So I've got x minus z, y is z plus 1, and z is z. So that means I've got an infinite number of solutions here. So that means I'm looking for, are they the same plane or are they not the same plane, but again, they have infinite solutions. So that will be a sheath. So if I just label these 1, 2, and 3, let's have a look at equation 1. These should be the same and they're not. For 1 and 3 here, the values would be the exact same because they've both got x's. 1 and 2, if x doubles, y isn't doubling, so that's not the same equation. And then 2 and 3, they're not the same either. So they're not the same equation that's been scaled up by a factor, and that will be both sides of the equation. Remember, if so one side scaled, they're parallel, they're not the same plane. If both sides been scaled up, then it is the same plane. So that is going to be a sheath. So when I did the last one, you'll see that I can't remember, I think I said it was a prism. It didn't look like a prism on GeoGebra, so I should have checked that. But it is going to be a sheath, so apologies. When you go back and it says it's not a sheath, it is going to be a sheath. And then if we have a look on GeoGebra, so these are the planes here, and you can see they all meet on this line here. So there's our sheath there. So let's have a look at our final set of equations. So determinant of those is 0 again. So it's singular, meaning it's got infinitely many solutions or no solutions. And then if we do our solver, we get no solutions again. So no solutions, meaning they are parallel or they are a prism. So again, check if any of them are parallel. So if is any of the left-hand side a multiple of each other for the equation. So if I have a look at equation 1 here, if I double x, double y, that doesn't work. Apologies, that's my phone. And then 1 and 3, so x, they would have to be the same, they're not. And then 2 and 3, if I double that, that doesn't work. So none of them are parallel, so that must mean it's a prism. And this one is a lot nicer to see on GeoGebra because I think the points are a little bit more spread apart. So hopefully we can see there. There you go. You've got a nice prism that's formed between those planes. You can see that really clearly. So you've got your lines of intersection of all three planes, and you can see that none of them intersect with the other plane. So that's why we get a prism. Last thing we're going to do is just have a look at this question, just put that into practice. So we have a system of equations here. So it says for each of the following values of k, determine whether it's consistent or inconsistent. If it's consistent, determine whether there's a unique or infinity solutions, and then determine the geometric configuration for those k's. So as it says here, if the system of equations is consistent, if the corresponding matrix is non-singular, its determinant is non-zero. That means it's got one solution. If the matrix is singular, remember, it could still be consistent because it could be it's got infinite solutions. Either it's a sheath or they lie on the same plane. So as it says here, if you eliminate one of the variables and the resulting two equations are consistent, then the system itself will be consistent. Because it has to be consistent with each other. I feel like I've just said the word consistent a lot. Anyway, let's have a go at part A when k is 0. So let's think about what equation we would get there. So for that one, so I've just written that out with k as 0 in there. So I end up with that matrix there, 3, 0, minus 6, 0, 3, 3, minus 3, minus 1, 3, x, y, z would equal 0, 2, minus 2. So I get a determinant there of minus 18. That means it is a, I don't know why I'm right, singular. It's a non-singular matrix. So it's non-singular, meaning it has one solution. So it isn't determined whether it is a unique solution. So it is a unique solution. And then the unique solution, we can just put that in our solver tool to find what that is. And I get the following solution. So I get that x is 4/3. Try that again. Y is 0. And I get that z is 2/3. So have I answered that question? So it says determine it's consistent. It is. Determine, so I guess I should also write that it's consistent, which we know because it's got at least one solution. So it's consistent, it has a unique solution, and we found the unique solution right here. And then identify the geometric configuration. Well, the geometric configuration is that they all meet at a singular point. So let's just write that. So, whoops. So the planes meet at a singular point. Okay, so that's the first one. So now let's have a look at part B. So part B is where k is equal to 1. So I'll just set up that equation now. So that's my matrix equation written out, and I get the determinant is 0. So therefore, I don't know about its consistency. It's either got infinite many solutions or no solutions. So now let's just put that in the solver tool to see if it's got any solutions. So for that one, I get that it's got infinitely many solutions. So it's consistent. I apologise for the awful handwriting. So it's consistent with infinite solutions. And now we need to consider, is it whether they're on the same plane, or is it that they form a sheath? So remember, if they're the same plane, they will form basically the same equation if we scale them up or down. So let's just have a look at that and just have a look at that matrix and see what happens with that. So for this first one here, let's see. So it doesn't look like with equation 2 that they are the same plane, because if I multiply, that doesn't work, no. And then if I look at equation 1 and 3, that would have to be negative, that would have to be, they're not, so 1 and 3 would not work, so they're not parallel. And then let's check 2 and 3. So they're not parallel either. So none of them, not parallel. So they're not the same equation. They are not the same equation. So they are not the same plane. They are not the same plane. So therefore, it must be a sheaf. That should say sheaf. So therefore it's a sheaf because they're not the same plane. And you can again prove that with algebra. So let's have a look at part C. So part C, this time our k is going to be -6. So I'll just do the equation and all that. So for that system of equations, I get that the determinant again is 0. So again, that either means we are working with infinite solutions or no solutions. So let's put that in on our solver tool to work out how many solutions it's got. So for that one, I get that there are no solutions. No solutions, which therefore means that they are inconsistent. There are no solutions to those equations, meaning they are inconsistent with each other. And again, if you wanted to prove that, so as it says there, eliminate one variable. If the resulting two equations are consistent, the system will be consistent. But if they're not, then that means they're inconsistent. So you can do that to prove that as well. But there are no solutions means inconsistent. So now we need to figure out, are they parallel or is it forming a prism? So if I have a look at those equations, can I see if they're parallel? So let's check equation number 1. So they're have times by -2. No, that doesn't work. So equation 1 and 2 don't work. What about equation 1 and 3? So I've made that a -3. No, they don't work. So it doesn't work for equation 1. Let's have a look at equation 2. So for equation 2 and 3, I think they might be parallel, because if I do -6 divided by 2, I get -3. Oh no, they're not. Actually, I changed my mind. They're not parallel because these are both negative, and then these change sign. Yes, if I've got that correct, those change sign. So no, they're not parallel either. So that's not parallel because it'd be divided by 3 anyway. They're definitely not parallel. I don't know why I thought they were. So they're not parallel. So therefore, they must form a prism. So no parallel lines. No parallel lines. That should say line. So therefore, it must be a prism. So that's how you think about those questions. So again, I would probably, for the consistency, use the algebra to prove that. And then obviously you can check it with the equations. But that is the general idea of it.